This is Paul Gregg. I'm going to make a video about some work I did with a high school locally. They were tasked with making spaghetti towers, and I did a bunch of work here and made an acceleration table so we could quantify uh, the testing of these. So a spaghetti tower is some kind of tower. These were made with spaghetti and hot glue. This is my acceleration table. I'll talk about it more. It's a spring-loaded uh, acceleration table. And then we had specific weights at the top on a platform that's 12 inches up. And we could use one, two, or three springs, and you pull it back to a certain notch in this angled uh, piece, and you let it go. And so we can get a variety of different accelerations, just 50 settings there between the number of springs, the notches, and the number of weights you put on it. You can get a lot of up to, I think, 65 newtons of force on the bottom. So this is the Spaghetti Tower Challenge. Um, Cardboard base, 12 inches by 12 inches, and then a 6 by 6 inch base that's supposed to be 12 inches high, and then it can be 16 inches high, the tower above that. You can see we have two of these weights. I made some weights. They're 475 grams each. Um, Construct it with dry spaghetti and hot glue. And then you're gonna, without the weights on it, weigh the tower, and that's one of the parameters. It's not just how well it does, but it's how well it does for how much spaghetti and glue you used. So that's the challenge. Um, the tower and the base are weighed, which is really an assessment of cost. The more material you use, the more costly something is, and you can't use if it's too expensive. It doesn't matter how good it works. Um, you can't afford it. So, especially in buildings like this. Um, the towers put on an acceleration table, and then increasing weights and increasing springs and increasing pullback distance uh, results in different accelerations, increasing, and you just keep accelerating until something breaks. And there's a kind of a there's a break where just one piece of spaghetti breaks. That's the first break, and if you want to, you can keep testing it at higher accelerations and see if at what acceleration the whole thing comes tumbling down. Of course, it's nice to have one thing break and the tower stay together versus a total catastrophic collapse. Um, so the first thing is to understand the problem. What are we trying to solve here? We're trying to make a spaghetti tower that can absorb the most amount of acceleration and the least amount of spaghetti and glue. When we think about it, this is all about earthquakes. There's lots of different loads in a real earthquake. They can be quite different, but what we're talking about is when when the earth that you're building is on slides sideways and accelerates back and forth. And the testing I'm doing is just one acceleration, and I'll go into the reasons why I like that. You could also do, most of these spaghetti tower contests I've seen online, even at colleges, the teacher just shakes the table. There's no quantified measure of how much it withstands, and I didn't like that. So I wanted something that you could quantify it. There are some people that have a real shake table that is has instrumentation on it. You can tell how much it's accelerating, and the frequency and the amplitude. And so most people don't have those facilities. So we're just talking about the horizontal accelerations that you'd see going back and forth. In an earthquake, when the earth moves to the left here, the building wants to move to the right. There's two effects here. If it was just a cantilever beam sticking up in the air, and that is it's flexing, so it's bending, but it's also shearing. So this is a kind of a picture of a cantilever beam sticking up that would be just doing bending, but it's also doing shearing. Okay, and that's an important thing in how you design your building is it not only has to take the bending loads, but it has to take the shear loads. And so we'll talk more in that. And this is what really happens. It's a combination of bending and shear. So it's like a big diving board stuck into the air and it's moving sideways at the base in an earthquake. I guess reading about the lateral forces in earthquakes, most of the damage comes from lateral forces. If you were on a fault line and that's where most common damage comes from, I guess, in reading about it. So when I was an engineer at Boeing, the key rule in design is think about your load path. What does this structure have to do? Form follows function. I think about the function and then I think about the form, what I'm going to build. I don't just start thinking of ideas. I think about where the load's going and wants to go and what's the most efficient way to do that. Um, when you make your spaghetti towers, if you just make them in rectangles and squares, you'll find they're very flexible. They don't hold much load because they're bending all over the place. A triangle provides some real good stability, and so you want to incorporate some kind of triangular members, and typically that's kind of a diagonal bar across there. And you want to think if I was loading this rectangle, if it was held on the ground and I was pushing the top of it over to the right, that top member would be in compression, and then these members would be in bending, and it would move a lot to the right. If I put this one diagonal member in here, which is in tension now in this load condition, then all of a sudden the tower becomes very strong and very stiff. And so think about and try to uh, think about your load path and think about which members are in tension, which members are in compression, and uh, and you'll design a better tower. So here's a simple tower. And if we were moving the shaker table to the right, the acceleration table to the right, then the weight at the top exerts a reaction force to the left. And so in this instance, this spaghetti here is going to be in compression. That's red. This is in tension. That's blue. This member here is in compression. I've drawn out which members would be in compression and which ones would be in tension. Of course, in a real earthquake, it shakes back and forth, and these would reverse. So compression and tension, they'd each have to take one. But um, in our case, if I'm going to just accelerate it in one direction, then I can design to that case. Typically, you're going to make these symmetric because the loads will go back and forth and fairly even. Um, a lot of people put a reciprocating saw or something like that on their shaker table. It works, but it's hard to quantify. It's hard to control the amplitude and frequency of the shaking, and it's hard to know what is really happening. It's hard to control it. You could put there's accelerometers in your smartphone, and you can get an app that lets you track the accelerations, but all the ones I've seen are very hard to control. And so it shakes a lot, and the spaghetti tower comes apart, and it's very difficult to assess that spaghetti tower to the next one, which was shaken a little bit differently or a lot differently. And so I thought about AC motors and doing that, and you could do that if you had the inclination. Yeah, you could instrument it and do a really good job of that. But something more simple is to just put some springs in the system, rubber bands or bungee cords, or in my case, metal springs. Pull it, compress those springs, or extend them, and then let it go. And there's one acceleration with my smartphone I can calibrate that, and or I can calculate it based on the forces in the spring and stuff like that, and the masses and everything. So with simple physics, we could do that. Well, the simplest thing to do would be to put the whole thing on a wall, constrain it, and then pull down on it until it broke. And that's just kind of a static load, but it would tell you how strong your spaghetti tower was, and that would be a good contest to do it that way. But in my case, I put an acceleration force, and then the weights are up here, and it acts like it's in an earthquake. Um, so engineering of spaghetti towers. First we got to find out all about the spaghetti. And I'm going to make another video about the actual testing I did and the research I did on finding the mechanical properties, the stiffness and strength of spaghetti. But for now, we can say we know what the length is. Most of it comes in 10-inch dry spaghetti lengths. The diameter, the weight, what's the strength? The other video will be about the tension, compression, shear, and bending strength of dry spaghetti. And then we talk about buckling, but we'll talk about buckling in a minute. Uh, and then joints, because the spaghetti tower needs to be at least 16 inches high, and the spaghetti is only 10 inches high, we're going to have some kind of bonded joints in that. And I'll talk about that. And I did some testing on it. You can look at different architectures. Is it better to have a triangular base? Is it better to have the biggest base you can? Is it better to slope the sides in? Or all kinds of questions about architecture. Um, and then what you do is you maybe sketch out all the ideas you have for what a spaghetti tower could look like, and then assess the weight of each one. What does the load path look like? How do you think it's going to hold up? Which members are going to be in compression, which is where they really want to fail because they buckle, and uh, and then consider how many pieces of spaghetti you want to use to to reinforce the buckling. And I'll talk about that. Here's some fabrication notes. When I constructed three of them. It's better to kind of take one side of your tower, draw some lines on a table, put it down and glue. Just be very careful to glue one side of the tower together, so you don't glue it to the table. I tried wax paper, and hot glue sticks to wax paper quite well. So just use as little glue as possible on one side of the horizontal, verticals, and diagonals, and then turn it over and reinforce that and with hot glue once that's dry. Then once you got the four sides, you can stick them together in an upright position. Um, so anyway, um, put them on the side. When the glue dries, turn it over, clean it up, and join the. And if you need longer than 10-inch members, you kind of make those ahead of time by doublers, spaghetti double sections. I'll show you. There'll be pictures of it. Think about which ones are going to be in compression, which ones are in tension. Um, you might need a lot more if they're in compression. You might consider bundling the spaghetti together when it's got higher loads, or putting cross members in so it's reinforced. So this is over here. Don't mind this. This is a 3-point bend test for the spaghetti itself. But this is my acceleration table. You can have one, two, or three springs in it. You pull this um, angle with holes in it back to a certain thing. There's a nail here. Put it on there and then just release it and let it go. Seems to work really well. You have the option of one, two, three, or four weights on the top here. And if you go through and you have one spring and you pull it all the way back as far as you can, and one weight up here, and that doesn't destroy the tower, then you can put two weights on it and start over, or put two springs on, or both, and you can get up to a wide variety of accelerations here. So there's a 6-inch by 6-inch cardboard platform. It has some cardboard borders on it, so that what you don't want in the test is for things to be moving around on the acceleration table, and so because that'll screw up the results. Um, so try to make this so this fits on here tightly and it fits in the on the table tightly. I made it so that it was a lip here. If you accelerate to the left here, then the 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 base is gonna lift off of the table. And so I have a little lip over the top there that doesn't let it do that. And so it kind of fits in there kind of tightly, and it worked really well. Mhm. I might try attaching a motor to this later and try to instrument it so I can do a shake table out of this. Oh, the key component here is the drawer slides. So this prevents motion in the, we'll call X direction, the motion of the drawer slides, and this limits the Y and Z direction. And so you want to kind of separate those things. If you just shake it all over the place, you don't know what you've got. So I made this table and then I put my smartphone with the accelerometer app on it, and I calibrated all these positions for up to three different springs, up to 12 different notches here, and four different weights. And so I have a lot of data on calibrating this, and I have some tables that go along with it. So this was one of the first runs where we do it, and this is the data from my smartphone app, which is an accelerometer app. And Physics Toolbox is what I have on my Pixel 7. And then you have to kind of attach your phone to the table fairly rigidly so it's not sliding around. And then takes, you just start the phone, start the acceleration taking of the data, let it go and see what happens. You can see there's X, Y, and Z. So in this case, Y was or sorry, this is TGF is the sum of all three. Here, FY was the direction. I put my phone sideways, so Y was the direction of the acceleration. And you can see the Z and X accelerations are there, but they're quite a bit smaller than the predominant one, which was the goal of the drawer slides. And I'm getting about almost -4 G's here from what I did here, probably two springs, it looks like. Okay, now these are the three tables, and they look complicated, but all this is when you're running the contest, you say, okay, I had a tower, we didn't have any weights on it, we went from all 8 positions, and it didn't fail. So we put one weight on it with one spring, and we went through the hole numbers, which is the pull length. Really, this relates to this. This is hole number. They're half inches apart, these things. So this was in millimeters. The holes were half-inch apart. So holes number 6 through 13, that's the pullback length. That's the number of G's and the force. And 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 so this is a calibrated table. Now, after I do this, and then I do the testing, and I go somewhere in here. The most spaghetti towers are going to break, and you write down how many G's it took and what was the force. The force is a certain number of G's, but the force means it might have had less or more weight on it, and so the force goes up when the G's stay the same. So, but using this table, the number of springs, the number of weights, which hole number I pulled it back to, and the weight of the weights that were on there, you pull it back a certain length, and I get a certain number of G's, and I can calculate the force. So this is the first one I made. I made 3, and we'll go through each one of them. It accelerated really nicely. It took a lot of load, it took a lot of weights on it. I think it had 3 weights on it in the end when it finally broke. And then 2 pieces of spaghetti broke, the ones in compression. And we can take take a look at the video. I don't know that. Okay. You saw it accelerated to the left when I released the little bar. And one piece it didn't, not a catastrophic failure, but it did really well. So, um, that equated to 4.83 Gs and 47 meters per second. And on the last page, I think I calculated the force in newtons. So let's go. This is after the test, before and after the test. It broke a compression member in buckling. And so the nice thing about this is you could repair this and retest it if you want to. This is the second tower I tested, and it went to almost 2 Gs and 11 newtons of force. I guess we can look at that one too. It only had one weight on it and one spring, so it's a much weaker tower. It was made with a different kind of spaghetti. There's thinner spaghetti and thicker spaghetti, and this spaghetti was pretty thick. So this is my third tower. And I didn't show, but the first tower weighed a certain amount, 130 grams. This is the weight of the cardboard and the spaghetti and the glue. The second tower is smaller. It only weighed 90 grams. And the third tower is 135 grams. I use the thinner spaghetti, but I use quite a bit of it. And this is the testing of my third spaghetti tower. Apologize for the video being that off. I think somehow the frame rate of my uh, smartphone camera interferes with the frame with the fluorescent lighting in my garage or something like that. But you can see kind of what happened. A few pieces of spaghetti broke. That one didn't, the test before that one was 2.19 Gs and 22 newtons force, two weights, two springs. So I do the test, then I go back to that table and determine these numbers because I've calibrated it with my phone. Okay. So this is the spaghetti tower testing summary. My first tower built with the thicker spaghetti actually has a hole in the middle of it. Well, in the spaghetti property testing video, I'll talk more about each of these spaghettis and the difference between them. Went to 3.5 Gs, 53 newtons almost. And now this is where I'm talking about that you just won't, it's not just enough that you built the tower that was the strongest. How much did the tower weigh? And then you take the capability divided by the weight and you get a number. And that's really the criteria score, the evaluation. So the tower that wins isn't necessarily the strongest one. It's the strongest one for its given weight. And that's how all engineering is. It's not, you're trying to meet certain criteria, certainly. But the best one if you have a lot of candidates that meet a certain criteria, which one of them did it at the lowest cost? And that's usually what you have to look at in engineering. So tower number one, tower number two, and tower number three. So tower number one did a lot better. The third tower I made with all the spaghetti here, the next best, and then the poorest tower was the one that was kind of the smallest and simplest. You can see the base of this one is only 6 by 6 inches. The base of this one, I tried to maximize that. And the base of this one is somewhere in between. This is actually the best one here. And it has to do with the buckling capability of those thicker spaghetti. But anyway, so I will produce a video about my buckling testing of individual pieces of spaghetti and bundles of spaghetti and lots of things like that. 3-point bend testing and some tension testing. And that's it. It'll be in another video. So that's it for today. Thanks.